In this segment, we're going to solidify what we've talked about in the past couple of segments about identifying enantiomers and specifying the absolute configuration of each chiral carbon within a molecule using the RS notation. So we are going to go ahead with some example problems here to make sure that we are all on the same page with coming up with RS stereochemistry assignments. So what we're going to be asked to do in the first example problem here in this problem solving session is to specify the absolute configuration of all chiral carbons within the molecule that we're going to draw. So we're going to specify the absolute configuration. When we say absolute configuration, we're saying that we can unambiguously specify what the orientation of those atoms around the chiral carbon are within three-dimensional space. We're going to be using RS to do this by specifying the absolute configuration of the molecule below. So we're going to go ahead and draw out a molecule here that has one or more chiral carbons in it. To get things rolling with this example problem. All right, so let's take a look at this molecule. Hopefully you recognize within this molecule we have an alkene functional group, that carbon-carbon double bond up top there. We also have an ether functional group, a carbon-oxygen-carbon bond showing up in this molecule as well. So let's go ahead and get started. First off, we need to recognize where our chiral carbons are that we can specify the absolute configuration of. To specify the absolute configuration, we have to have wedges and dashes shown. You can have an unidentified chiral carbon. A chiral carbon is just a carbon that has 4 different groups bonded to it. But if we're going to specify whether that particular chiral carbon is R or S, we absolutely need to have wedges and dashes shown to indicate what the three-dimensional shape of the molecule is relative to that carbon. So we've marked off our 2 chiral carbons within this molecule. And now our assignment is going to be to go in and specify each of those as R or S. So let's start with the chiral carbon on the right-hand side here. So that chiral carbon, we need to go in and to assign it as R or S, we're going to go in and use those criteria that we looked at down here that we went through in detail in our last segment. We're going to start by ranking the 4 groups that are bonded to the chiral carbon. After we've done that, we're going to orient the molecule so the lowest rank group points away from us, or we'll use that hack that we talked about in the last series, where if the lowest rank group pointed toward us rather than away from us, we could flip what we came up with as the assignment, R to S or S to R. And we're going to use that to go about assigning this molecule. So let's get back up here to this. So specify the absolute configuration of the molecule below. You could hit the pause button right now and challenge yourself to see whether you are able to do this on your own or not. That would be a terrific idea. So we have our chiral carbon there with a star on it, and we have to ask what that's directly bonded to. Well, it's going to be directly bonded to a hydrogen atom that we show as a dash, and that's going to be our lowest ranked group. So I'll go ahead and put number 4 on that just to get us off to the right start here. And then we have a carbon atom here that's a CH3 group, carbon atom here that's part of the alkene group, and a carbon atom here that is directly bonded to the oxygen, the ethyl group, and to a hydrogen. So, all right, looking at our chiral carbon there in red, we see that it's directly bonded to H, C, C, and C. In order to differentiate between those 3 carbon atoms, what we need to do is dig a little deeper. So we take the carbon atom from right here. I'm going to go ahead and put that like so, and then I'm going to make brackets. And within those brackets, I'm going to put the 3 atoms that carbon is directly bonded to other than the chiral carbon. So that carbon atom there at the end is directly bonded to H, H, and H, since it is a CH3 group. So I'm just going to leave that like so. We'll be comparing what's in the brackets there to what shows up in the brackets for these other groups. So here we have a carbon. That carbon is directly bonded. And we'll always have 3 things in the brackets here. So that carbon is directly bonded to another carbon. It's directly bonded to a hydrogen because there's a CH group right here. So I'll go ahead and put in the H. And then we have to ask what's going to be the 3rd thing that goes into the bracket here. The 3rd thing that goes into the bracket is going to be another carbon atom, because what the rule is is double bonded atoms count twice. Triple bonded atoms count 3 times. So double bonded atoms go twice into the bracket. So that's why we have within the bracket at this location C, C, and H, because the carbon that we show in green, we're asking what it's directly bonded to. It's directly bonded twice via the double bond in that alkene group, and it's directly bonded once to the H there. So C, C, and H is what we're going to plug in there. All right, let's go over to here. This carbon atom in green, we have to ask what it's directly bonded to. I'm going to put what it's directly bonded to in black. So always going to be 3 things in the brackets here. That carbon we list in decreasing order of atomic number. What it's bonded to oxygen, it's bonded to carbon of the ethyl group, and it's bonded to a hydrogen, which is implied there. So O, C, and H. Now what we will do is we will take these 3 groups and we will compare the atoms that are present in each of those brackets. So we have carbon, carbon, and hydrogen to compare to HHH or OCH. We're basing this comparison on the atomic number of the highest group that's in those brackets. So of all the brackets, our highest group is the oxygen right here, and so that's going to be the highest ranked group. So we'll call that number 1. Second highest ranked group, now we have to differentiate between our CCH and our CHHH. Hopefully you recognize carbon has a higher atomic number than hydrogen, so this is going to be group number 2 is coming off right here, and group number 3 is our methyl group right there. We already said that group 4 was our hydrogen that points away from us. So now we orient the molecule so that the lowest ranked group points away from us. The lowest ranked group here is the hydrogen, and much to our joy and happiness, that hydrogen is already pointed away from you. So all you need to do now is go from 1, the bond that leads over from the chiral carbon to number 1, through the bond that leads to number 2, over to finish at the bond that leads to the 3rd highest ranked group. Take note of whether the clock that you've drawn, the circle, goes in the correct orientation of the clock, or whether it goes opposite the correct orientation of a clock. It is moving the same way as the second hand of the clock, and so therefore it is clockwise, meaning it is the right direction, the correct direction for the clock. So we're going to go ahead and put that in as an R chiral center. We have a second chiral center in this molecule at that ether group that we need to assign, and that's what we're going to do now. So I'm going to just move the page up just a little bit here and over so that we can go in and redraw the molecule to allow us to specify that chirality in a version of the molecule that I haven't scribbled all over yet. So we've redrawn the molecule here, like so. Now what we're going to do is go in and assign the 4 groups that are directly bonded here at this carbon atom. So at this carbon atom, we have directly bonded, I'm going to put in green here, an oxygen, a carbon, and our hydrogen has to point toward us as a wedge, because that's the missing part of the tetrahedron. So ranking these 4 groups based on atomic number of the first atom we see, there in green is our first atom we see. We have oxygen, carbon, carbon, and hydrogen. Oxygen we can clearly rank as number 1, highest atomic number. Hydrogen we can definitely rank as 4, lowest atomic number, and now we need to figure out what to do with those 2 carbon atoms. So our 2 carbon atoms, the one right here, we'll go ahead and put that carbon in green, and then in brackets in black I'm going to write the 3 atoms that that carbon is directly bonded to other than the chiral carbon. So that carbon in green is directly bonded to another carbon. That's the carbon at the very end there of the CH3 group. It's directly bonded to a hydrogen, and it's directly bonded to another hydrogen. So CHH will fill in there. Our other carbon atom that we need to assign is the one right here. So I'm going to put carbon, and then keeping with my color scheme, I'm going to put in black brackets here the 3 atoms that carbon is directly connected to. So that carbon is directly connected to 2 carbon atoms, carbon and carbon. That would be the carbon of the methyl group right here, and the carbon that goes to the alkene group here. And then that carbon is also directly bonded to an H to fill the octet of that carbon. So now comparing what we have in brackets for these two carbon atoms. You have CHH or CCH. Carbon-carbon hydrogen definitely outranks carbon hydrogen hydrogen because we have this carbon right here, whereas up here we have a hydrogen. Carbon outranks hydrogen, and so therefore we're going to classify this as having a higher rank than the other group. So we already established group number 1, so this has to be number 2, and then this group would be number 3. So now what we will do is we need to assign the chirality of this molecule as R or S. We notice that the hydrogen here, the lowest ranked group in this case, points toward us rather than away from us. And so we can't just straight away draw our clockwise or counterclockwise circle and assign directly based on that. What we can do is we can go from 1 to 2 to 3, and we can declare that the stereochemistry is opposite of what our arrow indicates, since the orientation of the hydrogen is opposite what it has to be in the definition for calling out R and S. So here, our arrow goes clockwise, which would suggest S, but in actuality, the stereochemistry has to be R because of the fact that the hydrogen is pointed toward us rather than away from us. So we'll go ahead and call that an R chiral center. The alternative way of doing this would be to actually rotate the molecule around and redraw it so that the hydrogen is physically pointed away from you. If you go that route, you should still come up with R as the configuration. The only way to change the configuration from R to S would be to actually do a chemical reaction where you physically tear apart bonds and put them back together in the other three-dimensional orientation. Any rotations that you do of the molecule or flipping it over won't change the R or the S at any location in the molecule. So with this, we can describe the configuration of this molecule as being RR. Each of the chiral centers in the molecule has the R configuration. In this example problem, what we are asked to do is provide the IUPAC name for the following molecule, including stereochemistry. So when we say the stereochemistry of the molecule, what we're indicating is that at the beginning of the compound name, we need to indicate the designation of R and S. And the way we do that is if we look back here at the handouts of information for providing RS information. To incorporate the stereochemistry into IUPAC names, what we're going to do is at the very beginning of the name, we're going to indicate the stereochemistry assignment in parentheses. So for example, if the molecule name was 3,4-dimethylheptane, and we wanted to specify the stereochemistry at the chiral carbons 3 and 4, right before the name we would put in parentheses here 3s, 4r to indicate the number of each carbon atom that's chiral, carbon 3 and carbon 4, and what the absolute configuration at each of those positions was. And then we would put all that into parentheses at the very beginning of the name and separate that from the latter part of the name using a dash. So that's what we're going to do right here. So this requires that we be both proficient at coming up with IUPAC names and at assigning stereochemistry. And if you're a little bit weak on assigning IUPAC names, you can go back and review the tutorial on naming organic molecules. Specifically, we did it for naming alkanes. So we're going to go through and come up with the stereochemistry and the IUPAC name. So first things first here, let's just get started by coming up with the IUPAC name sans stereochemistry. So we're just going to come up with what the parent name and the branches are. First off, we have to find the longest carbon chain in this molecule, and that's going to become the parent name of the molecule. So look for the longest carbon chain here and identify that. Please, you are welcome to hit pause to find that longest carbon chain and make sure that it matches what I come up with. Okay, looking for the longest carbon chain in the molecule, that is the longest carbon chain that we can trace through without having to lift our pencil or backtrack. What we find is that we could come from over here, tracing the longest pathway through that we can without lifting my pink pen there. And that's going to be our longest carbon chain, which will allow us to come up with the parent name for the molecule, which I'm going to put in red since I've highlighted through that in pink. That longest carbon chain, if you count up the number of carbons there, you should come up with 8. So I'm going to plug in the name octane. I'm going to try to write that all the way over here at the far right so that I don't run out of room, hopefully. Octane is our parent name for the molecule. We need to decide how we are going to number octane in the correct orientation. Remember that we always number starting from the end closer to a branch. And so here, the end closer to a branch is going to be this end. Carbon 1, 2, 3, 4, 5, 6, 7, and 8. So now what we need to do is specify the names of the branches that come off of that longest carbon chain and where they are located. I'm going to highlight those branches in blue. So we have a methyl branch at carbon 2, methyl branch at carbon 4, ethyl branch at carbon 5, methyl branch at carbon 6. Let's go ahead and plug those in. I'm going to plug them in blue into my name. So we have ethyl and methyl. We need to put those in alphabetical order. Methyl comes after ethyl in the alphabet, so methyl is going to come after ethyl in the name here. So methyl octane, and we need to specify how many methyl groups we have by using the terms di, tri, tetra, etc. In this case, we have 3 methyl groups. We're going to call this a trimethyl group, and we always have to specify to indicate what constitutional isomer we're dealing with here. We need to specify where those methyl groups are located. They're located at carbon 2, carbon 4, and carbon 6. We're going to call this 2, 4, 6 trimethyl octane. That takes care of our 3 methyl groups. We also have that ethyl group at carbon number 5, so I'm going to plug that in as a 5 ethyl group. And now this is nice because it gets us in alphabetical order. Ethyl comes before methyl. Remember, we ignore terms like di, tri, tetra, etc. that tell us how many of a particular group there are when we're alphabetizing. So we've got our full IUPAC name now in place except for the stereochemistry. Now the fun begins. We need to specify what the stereochemistry is at each chiral center within this molecule. And we have 3 chiral centers within the molecule, so what I'm going to do is put at the front of this in brackets and then use a dash to separate our parentheses from the rest of the molecule. Our chiral carbons are at carbon number 4 is a chiral carbon, carbon number 5 is one we can specify, and carbon number 6. So I'm going to go ahead and fill in my parentheses here. 4, I'm going to leave a space to assign that number 4 as RS, 5, leave a space to assign it as RNS, and 6. Now we go in and come up with the the absolute assignments of these 3 groups. Okay, so let's start with carbon number 4. So carbon number 4 is right here. That's our chiral carbon there. We're going to look at the 3 groups that are bonded to it. So we have a carbon atom here, and carbon atom here. We also have a hydrogen directly bonded to that, which fortunately for us is pointed away from us. So we'll go ahead and fill that in too. Hydrogen is going to be our lowest ranked group, so I'm going to go ahead and put that in as number 4. Now we need to rank these 3 carbon atoms. We do that by looking at what atoms each of those carbons is directly bonded to. So looking at this carbon right here, I plug in the carbon, then I'm going to put in parentheses in black here what 3 atoms that carbon is bonded to. It's bonded to 3 H's as we go away from the chiral center. So I filled that in. I'm going to do the same thing for the other 2 carbons so that we can compare these 3 carbons to one another and come up with the rank of each group as a result. The carbon atom that we're focusing on now, we ask what 3 atoms it's directly bonded to. It is directly bonded to one other carbon going away from the chiral center, and it's a CH2 group, so it's directly bonded to 2 hydrogens. All right, we come onward to our next carbon. That's this guy right here. This carbon that I'm showing in green, we asked what atoms it's directly bonded to. Put those in brackets. It is directly bonded to carbon, carbon, and hydrogen as we go away from the chiral center. It's directly bonded to the ethyl group carbon below it, and it's directly bonded to the carbon to its left there going away from the chiral center, and then there's that H to fill the carbon's octet that we have implied there. All right, so now our task is to compare what we see in brackets for these 3 positions here, here, and here, as I've highlighted or underlined rather in red there. Okay, so looking at these, in one of the cases, the highest ranked group we have bonded is a hydrogen, and the other 2, we have carbon and carbon. So we can immediately say that that group that's bonded to a hydrogen rather than a carbon is going to be the lowest ranked out of these 3, which puts it at number 3. Number 4 we already assigned as our hydrogen. Now the race is on for positions ranked 1 and 2. And when we look at and compare our 2 remaining candidates, we have a carbon here on this one that I'm circling in blue. The other at that position has a hydrogen. Carbon has a higher atomic number than hydrogen, so that means that this group on down below is going to be our highest ranked group. So I'm going to put a number 1 there. And number 2 then comes to right here. Okay, so now on to the home stretch for this one. We're going from 1 where we start at bond leading to number 1, we go through the bond that leads to number 2, and we come over and finish at the bond that leads to number 3. So the arrow that we've drawn here is a clockwise R arrow. So I'm going to label that chiral carbon as R. And within the carbon chain, that was at position 4 of the carbon chain. So we can specify in our name that this is a 4R absolute configuration. Okay, onward to chiral carbon number 5. I've kind of created a mess of the molecule here and labeling it up at carbon number 4. So I'm just going to, hopefully as quickly as possible here, redraw our structure so that I can then go in and specify the stereochemistry of carbon numero 5. So we're going through our practice problem here, and you should definitely be proficient at doing problems of this level of complexity. The worksheet that goes along with this chapter has additional example problems that should give you the practice you need to get really fluent in the language of R and S stereochemistry. Okay, so our next task here is to assign the chirality at carbon number 5 of our chain. That's this carbon right here. We're going to go through the same process that we did at carbon number 4 to come up with that. So in green, I'm going to put the groups that are atoms that are directly bonded to carbon number 5. It's a carbon here, a carbon here, and a carbon here. And our hydrogen is also directly bonded, and that's pointed away from us. I'm going to put the number 4 on that. By the way, you're totally welcome to bring highlighters, colored pens, etc. when you're solving problems like this in exams and things. It can be a really useful tool for keeping track of who's who and who's where. So, all right, in green we have color-coded our atoms that are directly bonded. We run into a problem, much like we did before, that we have 3 carbon atoms here, and we need a way to differentiate between those 3 groups. So what we do then is look one more atom down the chain in each of these cases. So this carbon, we can then put in brackets what it's directly bonded to. It is directly bonded to carbon of the methyl group, directly bonded to carbon of the chain, and directly bonded to an H. So we filled in that position. We do the same thing down here, this carbon, and then in brackets we put what it's directly bonded to. That carbon is directly bonded to another carbon of the methyl group and 2 H's. So we filled in that. And then I'm going to draw another green line here to connect to this carbon, put in green that carbon, and then in black what it's directly connected to. It is directly connected to a carbon of that methyl group. It's directly bonded to the carbon of the ethyl group going away from the chiral center, and it's directly bonded to a hydrogen. So now we come up with the ranking of the 3 groups that we have just outlined here and highlighted in red. The lowest ranking of those is going to be the carbon hydrogen group, because those hydrogens are lower ranking than the carbons that are in the corresponding positions for the others. So I'm going to go ahead and rank this group, our ethyl group here, as number 3 in our ranking, because of the fact we have CHH appearing here versus CCH or CCH here. Okay, so we've taken care of that assignment. Now we need to differentiate between our 2 carbon atoms here that are both bonded to CCH. So in order to do that, we need to move another spot down the chain in order to compare the atoms that are bonded at that location. So what we're going to do here is we're going to just keep going down the chain until we find a place where we can differentiate between the 2 groups. All right, so onward with the fun here. So we were at this carbon in green, and we asked what it was directly bonded to, and we couldn't tell the difference between the 2 carbons that we still have highlighted in green here. So what we do then is move another spot down the chain to right here or right here, and we compare what's directly bonded there. We would continue doing this until we reach the first point of difference, the first location in the molecule where we can tell the 2 groups apart. So our carbon in red here, we're comparing the groups that are bonded at each of those positions. So we go ahead and do our carbons, and then we put in brackets what each of those red carbons are directly bonded to. And we take one of those two red carbons. I'll do the one on the upper right first and ask what it's directly bonded to. It's directly bonded to one carbon, and it's a CH2 group, so it's directly bonded to two hydrogens. We come over to the other carbon. We ask what it's directly bonded to. It's directly bonded to a carbon of the methyl group, and it's directly bonded to two hydrogens. Can we tell these two groups apart now? So we have a carbon directly bonded to carbon, carbon, and hydrogen. And the comparison is with a carbon directly bonded to carbon, hydrogen, and hydrogen. All right, so we still can't tell them apart. So what we need to do then is go one more step down the chain to tell these groups apart. So that's going to bring us to right here and to right here. And hopefully now we'll be able to differentiate between the two groups. If we reach the very end of the molecule in both directions and we can't tell them apart, it means the two groups are identical, and therefore the chiral carbon is actually not chiral. You made a mistake somewhere along the way. All right, so that's not the case here, because in one direction we've reached the end of the chain and the other one we haven't. So our carbon on the right, we ask what it's directly bonded to, that carbon in yellow. Put that into brackets. So that carbon is directly bonded to carbon, carbon, and hydrogen. Our other carbon, as we work away from the chiral center at the other end of the molecule, that carbon in yellow is directly bonded to three hydrogens, H, H, and H. Okay, so now we're to the point where hopefully we can tell these apart. So we have C bonded to H, H, and H versus C bonded to C, C, H. Carbon outranks hydrogen, and so therefore that group that's going to the right is higher ranking than the one going toward the left. So therefore the highest ranking group, with much ado, is going to be this one. Second highest ranked group is this one, and we pretty much had to go through most of the chain to find a point that differentiated between those two. And so that's what we did, is we went one atom at a time down the chain, kind of painstakingly, to find the first atom that we can use to differentiate between the two groups. And so going from 1 to 2 to 3 here, we start with the bond that leads from our chiral carbon to number 1. We pass through the bond that leads to number 2. We finish up at the bond that leads to group number 3. That takes us running counterclockwise. That means that we can go ahead and assign this chiral center as the S chirality for carbon number 5. So we'll go ahead and fill that in to the name. So with that, only one chiral carbon remains to be assigned. That's at chiral carbon number 6. So what I'm going to do is just redraw the structure from up top here down a little bit below so that we can get an uncluttered version for solving this. What we'll do is focus in at carbon number 6. That's the carbon that has the red dot on it. We're going to go ahead and assign the priority of those 4 groups that are bonded to that carbon the same way that we have before, keeping in mind that the hydrogen is still pointed away from us right here in yellow. Ranking those 4 groups, the hydrogen is going to come in last, so I'm going to go ahead and put the number 4 on that. Then we have to compare our methyl group as our wedge there, ethyl group, and then the rest of the alkyl group that's there. So if we take a look at the relative rankings of these, what you should find is that the highest ranking group is going to be right here. Second highest ranking is that ethyl group. Third highest ranking is the methyl group. So now we go from 1 to 2 to 3, takes us 1 through bond number 2, ending up at bond number 3. Takes us clockwise, keeping in mind that the hydrogen is pointed away from us. That means that this is going to be the R configuration there at carbon number 6. So with that, we have the complete name of this particular molecule, including the stereochemistry of all 3 chiral centers.